So this is a lecture where we will discuss finite chain of atoms, and the course is still solid state physics. So now that we have solved a one-dimensional monoatomic and biatomic lattices, we will look into the case when we have still periodic lattices, but now they will consist of a finite number of atoms. And what we will learn is that then the solutions become discretized, and this arises from the fact that we have periodic boundary conditions, and this then means that we don't have a continuum of solutions or states anymore. And this is actually a piece of a physics that was found to be absolutely necessary to correctly calculate the heat capacities of solids. So this is in fact a very important thing we must do in our treatment of lattice vibrations. So we will improve the model and we will consider a finite chain of atoms. And the trouble we would have otherwise that, for example, our system, if it would have an infinite number of atoms, it, in principle, for example, would have a possibility of storing an infinite amount of energy. And this is often a bad case because we haven't found such materials in real life, so that we know that there seems to be something wrong in the model. And we will learn soon that this treatment results in discrete or quantized lattice vibrations. And that's why we are calling them phonons. So essentially these lattice vibrations we're dealing with, they start behaving quasi-particles. So like as an emergent phenomena in a lattice, and then it behaves a little bit like a particle in there, but it rises from the kind of periodic nature of our system. So how we will proceed is that we will impose periodic boundary conditions in our system. So essentially, when we are looking at the displacement of all of these atoms, and especially the S atom, US, then we would see and say that this displacement should be equal to the displacement of S plus nth atom. So we have a periodicity of n atoms that we are looking at here. And we will now see how this changes our treatment. So mathematically, this periodic boundary condition that we have, it corresponds to this equality. So U, the displacement of the atom S plus n, must be equal to the displacement of the S atom. So it's simple as that. That's the periodic boundary condition that we have. And now we will look what this implies to our subsequent solutions. And we will see that then this simple equation actually discretizes our system, and this is very, very groundbreaking for the implications point of view. So we have n atoms in the periodic chain. N can be quite a large number in practice, and now we want to see what happens for the displacement. And the form of a displacement was found to be that US equals to the amplitude of displacement U times exponent I KAS times omega t. And then we just mindlessly start plugging in this into our periodic boundary condition. So we see that US, and this is equal to US exponent I KAS minus omega t. This must be equal to the US plus n. And then we place, instead of s here, we place into the argument of the exponent I Ka S plus n minus omega t. And we should have u's here. So this should be actually like a u, the amplitude of the oscillation, and here we should also have the amplitude of oscillation. And this is then equal to the u S plus n. So we are just essentially invoking the periodic boundary condition that we said that our material now has, our system has. And this then means that the amplitudes are equal. That then what follows is that then the exponent IKAS must be equal to exponent IKA times S plus n. So essentially the frequency contribution vanishes, looks exactly the same, and the amplitudes of oscillation are the same. So what is left over is this exponent IKAS on the left hand side, and the same on the right hand side. And we can move the terms around, and we see that in fact this IK AS also vanishes, and what is left is that we have I exponent I k a n, where n was the number of atoms in our periodic system that must be equal to unity. So this is the condition we have now found that restricts our solutions. And this condition, due to the periodicity, it's this. And by recalling the properties of the exponential function, so like basically we can tell that the argument must be a multiple of 2 pi, then we see that this condition is in fact equal to the case that the amplitude of the wave vector k must be equal to 2 pi divided by a times n times m, where m is an integer. So essentially, like we already covered this in chapter 1, when we have this kind of condition, this is unity, we see that then what we have inside the argument, kan, this must be a multiple of 2 pi, and that's it. So that's why we have this like kan on the left-hand side, and then 2 pi m on the right-hand side, and then we just solve this equation with respect to the k, and that's it. And this means, when we look at the equation, that in fact our wave vector k is discretized. And this is a big deal. So it may not seem much, but in fact this is actually important. M is an integer, so k can only get very discrete values depending, of course, on what is the a, the lattice constant, and what is the n, how large is our n. And we will note here that we are still restricting our treatment to the first Brillouin zone, and there the only n different case, and we could say that phonon modes in this Brillouin zone fit now inside each of these dispersion branches. So this is then what happens. And I will now show this, what this means using a picture. I hope this helps. So we have now discretized our wave vectors. And this means that this dispersion relation omega k, it's not actually just a continuous function, but it's actually like a set of points, discrete points in the Brillouin zone. And I'm now plotting a case where I'm dealing with a monoatomic lattice, and when n is 16. So we only have 16 atoms in our periodic system. And these black dots would be the locations where we actually may have, what kind of lattice vibrations we may have. So we do not have infinite possibilities what kind of lattice oscillations we may have, but we only have like a few given amount dictated by the number of n. And of course, this case, n equals 16, like we see that we are actually having a hugely discretized, like allowed lattice vibrations. This looks very bad, but in reality, when we are putting like a very large numbers of n, we see that even though we are dealing with a discretized system, it looks almost like a continuum of states. So maybe like this may not sound like a big thing, but in the end we will learn that this is actually very important when we are actually calculating the macroscopic properties, the macroscopic thermal properties of our system. So this is what I wanted to say here. So like now we have moved away from infinite chain of atoms into a case that we actually have a finite chain of atom, and now we see that we in fact have a discrete oscillations that may reside in our periodic piece of a solid. And because of this fact, like we can actually in fact quantize our lattice vibrations. And because we can do that, we can then start speaking of phonons. So we can start speaking of lattice vibrations as quasi-particles of our system. But more of that in the upcoming lecture when we are going there. So I thank you for listening this lecture, and please stay tuned. We will soon understand everything there is to know about lattice vibrations for now. So thanks and bye-bye.